Okay, so this is the lecture 4. Lecture 4. And I turned this class into I called it functional analysis earlier. So um, now I gave it a different name. See, like one of the difficulties I had was trying to uh, I was trying to teach this thing to students with like less background. For example, people who haven't done um, functional. So the now this course, this is call it MC 410, and call this thing lattice view of algebra and geometry. Okay, and then functional analysis is just MC 304. This is just the usual textbook course, and and you have to follow these two things at the same time. Uh, you can of course use. It's better if you know MC304, but it's okay to follow these things parallelly, because I'd be spending more time on the lattice material at first, so you can like catch up with you learn functional analysis stuff on the side. Okay, now, so let me recall where we were. So we were doing something like, so this is, there is concepts in this side, let's call this thing space. And then concepts in this side, algebra. And then concepts in this side, lattice. Lattice or like partial orders, right? And uh, we are like planning to kind of go back and forth between these these different viewpoints, and we'll be able to have like basic maps, like 6 of them, and then if you have like more structure, can you bring it to the other side with more structure, and so that's the plan of the game. Okay, so and at the end of lecture 3, uh, I gave a overview of what you're gonna do. Okay, and now you can call the first 3 lectures as just introduction. So what we did in here, in the first 3 lectures, basically we built up the tools in here. Okay, we built up the tools in the, okay, let me know, gives me a thumbs up if you can see the screen, what I'm writing. Sometimes when I uh, switch to different, okay, so if in any case, if you cannot see it, then just let me know immediately, okay? Okay, now, uh, so now let's think about this as kind of now we are going deep into each of these topics. Okay, so we'll start here. So far we have done the, we have given the, studied the main tool in the lattice side. That's basically like the Sohn's lemma. And now then in the lecture 3, we gave like a whole bunch of definitions. And now we are going to dig into these things. Okay. So today, what we're going to do, the topic is directed sets. So limits. Limits in topologies, and then nerve. So let's start with the back to some pictures. We have the idea of a sequence. And we know a sequence, we write it as in going from 1 up to infinity. Okay? And what really, what's happening here, we have a map, let's call it A, from natural numbers to, let's say, complex numbers. If it is a complex sequence, that's what this thing is. Okay? And so this kind of tells you like kind of which direction that you are interested in, like, n goes to infinity, right? So we go, okay. And this side, typically we have a way of measuring the closeness. Okay. And well, that's one picture. And then later on, if you have a function from set, and this is what we do in analysis, let's say in Rn to Rn, something like some open regions in there, and then we can talk about point x here, and then you have xn goes to here, and we have yn, let's say f of xn, and then it goes to y. Okay, so you have things like we talk about limit n goes to infinity f of xn is y. We have seen these different types of stuff. And then also you learn something called direct limits. And yeah, you can take limit this way of like some groups. We have a chain of groups, and then there's something called direct limits. Okay, and in there kind of what's happening, there's a notion of limits in where your objects are like objects from some category, and then we have a way of let's say G1, we have these homomorphisms, and then if you have a chain of these things, then there's a notion called direct limits. So what I want you to notice is there are two things going on, okay? So there is the set where this guy, there is something in here, okay? And also that's the same thing in here too, right? But in here, kind of we can, when you have a topological space, we can talk about limits at different points. Okay, so but in here you have like only focused on the sequence. Okay, and in here you want to think about we have like this let's say maps between these objects, like that maps the things of like arrows, that kind of gives you the like the direction. And now instead of like complex numbers, but now we have groups. Okay, so we have I think I convince you, like I have a set A, and then we have some stuff. Okay, so this stuff can be like complex numbers or like groups or whatever. Okay, and then uh, this one has some order properties. Okay, that's kind of the roughly the idea, and we will build up on this thing. And yeah, so uh, let me talk about. So now we're going to give the definition. It is, I mean, it's a little bit general, so it's but it's not very difficult. Okay, so the definition, directed sense. So A is then equal is a partial loaded set, poset. Uh, with the property uh, for all A and B in A, there exist C in A such that and B is less than or equal to C. Okay, so note A we are not assuming that A AVB exists. Okay, so remember, like this is just a partial loaded set, and we are not assuming that this is a lattice. Okay, we are not assuming the joins, or we are not assuming the meets. Okay, so and but if you are in a situation like that, then you can take this C to be so C is we can't say that C is A union B. Okay. Okay. So here is an example. So we have A and B here, alpha, beta, and you have a C here. So setup is like if you have A So this picture means like stuff in the above are bigger than stuff in below. Okay, so in here is less than or equal to alpha and so on. Okay, and in this picture, if this is your offset and this one doesn't have for A and B doesn't have A, B doesn't exist because we have like two candidates for it. And okay, and but in this case, this example is a directed set. Okay, so in the directed set, what you care about is you have two things. You want to have one element that's bigger than both A and B. Okay, so the might not have the smallest element that's bigger than A and B, but you have an element that's bigger than A and B, and that allows you to kind of keep going. And again, like this picture tells you that if you have a kind of a top for the partial loaded set, that means you have a maximum element, then it is automatically a directed set. Okay, so this is the setup, and this kind of gives us the direction where to go in these examples of limits. Okay, so for example, the integers, it is a directed set. It's actually anytime you have a well-loaded set, it's a directed set. If you have a total order, then it's a directed set. And okay, so let me give out some examples. So integers is a directed set and well-loaded sets. Just even just a total loaded set. Okay. And then so have you seen the definition of a general topological space? Have you? I know that your voice is not working, but can you give it a chat? Yeah, okay, so you have seen the definition. Okay. Now, so the example here, so let X star be a topological space, and we take a point X, we point in capital X. Then you have A of X. This is U in tau such that X in U. Okay, so these are the okay, you're raising the hand. Let me post the. Looks like you have a question. Oh no, it is my hand that's raised. Okay, you don't have a question. Do you have a question? Okay, you don't have a question. Okay. So this verify that AX is a directed set. Okay, and when you talk about limits in topological spaces, like if you have a limit that goes to X, that means you kind of going through this directed set, and this is also called X is called a neighborhood basis index. Okay, let me give you the for somebody who hasn't seen the topological spaces. So if in the case of when xt is a metric space, and in that case you can talk about this AX, which is balls centered at X with radius R, where R is positive. This is example. It's a directed set. Okay, and okay, it is a question. Have you seen the definition of a basis of a topological space? Okay, so you have seen the basis, that means you have seen a sub-basis. Okay, this is great. Okay, so let me give you a little problem then. So like all these examples are actually if you look at this in topology, in general topology, so we have what we call wait. So okay, so this word is not the neighborhood basis. Okay, so this is the like, so this is AX is called so U in AX is called a neighborhood of X. Open neighborhood with X. And so in general topology have neighborhoods like A of X, that's like all the neighborhoods. And then you have a notion of a neighborhood basis. Neighborhood basis is a neighborhood basis at neighborhood basis at a point X in capital X. So you have X tau is a topological space. Neighborhood basis is is a collection. It's a collection. Let me call it. Call it A of x, such that B of x. Such that for all u in A of x is the this guy, like all the neighborhoods. Now when you have a basis, then what we have is this. If you take any neighborhood, there exists a element b from bx such that b is inside u. Okay, and you can show that not that not that when you talk about limits, we don't have to use the full neighborhood basis. You can still work with the we don't have to work with all the neighborhoods. It's enough to work with the neighborhood elements from the neighborhood basis. So this would be examples of example would be like balls with radius 1 over n. Okay, and then you can show that this bx is also it's also a directed set. Okay. So if you go from the you would go back and forth between the like what is the analogous concept in general topology for the directed set. That would be so we're looking at this I mean, these two things are very related. Okay, now let me write bunch of things maybe once again. So it's been like several weeks since I prepared these lectures. It's okay. Okay, so now let's. Do you know a sub-basis for topological space? Yes, no, maybe. Okay, so now, so let me record the definition. Uh, uh, a collection of subsets. We call it B delta. It's called a subbasis if okay, there is the notion of subbasis of a topological space. Okay, let me write that down first. And then you have another version. If you have a collection of sets that starts off with some properties, then you can construct a topological space by taking finite intersections and then arbitrary unions. Collection of subsets is called subbasis. B delta is a subset is a subset of topological space X star if for all u in tau there exists B1 up to Bn in here such that B1 intersect Bn is inside U. In other words, we have this collection B delta, but if you look at all the finite intersections, let me add the point two. You have open sets and X in U, then you can have a point like this. I think this is the definition for a subbasis. And okay, because if you have just a collection that doesn't if you have just create empty sets when you have this intersection, then that's no use. So note that this B given by intersection I equals 1 up to n bi for n greater than or equal to 1, and bi is in b delta, where I equals 1 to up to n is a basis. And then so I would compare so in the case of the these directed sets, what the role that they're playing the role of the this subbasis, but we're not assuming the intersections exist, because the intersections play the role of the V. Let me write exercise here, and I'll move on. I'll write an exercise in Piazza around this point, okay? What I really want what I'm really after is to kind of let me try it a little bit. Okay, so this is what I'm trying to do. Okay, so we have a topological space. Okay, so this is, let me draw it in here. So the topological space, as you know it, lives in here. Okay, and directed sets lives in here. Okay, and kind of know how to go from here to here. If you have topological space, and these examples will tells you the directed sets that you obtain by looking at all the neighborhoods, or by looking at all the like a neighborhood basis at a point, or neighborhood subbasis at a point. That would give you that would extract what is the index set when you talk about the limits that goes to that point. Okay, so this part is easy. Okay, now I'm trying to go the other way. Kind of gives you the gives you the kind of where does this directed set fits in the topological space picture. Okay. So what we want to do is kind of define the concepts in here in terms of you have like what is the properties that you have for a topology. If we just we write those properties in terms of the partial orders, okay, and then when you keep doing that, and then you'll build a map from in the topological space setting. You have what is a topology, what is a basis for a topology, what is a sub-basis for a topology, okay, and then these would satisfy different types of axioms in the lattice world, okay, and what I'm trying to get at is if you have the notion of a subspace, sub-basis, but the point is like sub-basis is for a topological whole topological space, not for a point, okay, so the I think what we have here, directed set corresponds to the kind of one point version of the sub-basis. Okay, so let me so the kind of the area for this thing is call it like pointless topology, meaning you don't talk about the points, but you do topology, and what you're doing is you carry out the whole operations just using the this some sort of partial loaded set with some axioms. Okay, so let me write a definition, but this definition is not standard. Okay, and so what we're trying to do is let L tau be a partial loaded set uh, uh, such that okay, so what are the axioms for the topological space? We have a whole set and the empty set is in there. So the whole set plays the role of 1 and 0 exists in L. So the 1 is the top element and the 0 is the bottom element. And then the second property, and of the let me call it topological lattice. So that's what I'm saying, that this definition is not standard. Okay, I think when I was looking at it, they have different. Actually, there's this like whole fields of study, areas of math that does this. Okay, and whole set and empty set is in here, and then the second property is if we have it's closed under finite intersection. So that means if we have A and B in L, then okay. Okay. Uh, we have, what was the notion for the, so we have subset F in L, then this guy exists. Okay. So these are the definitions or these are the definitions for a topology, and writing it in the lattice side. So now we so the so in the case of a directed set, definition for a directed set, what we have, we don't have one, and we have a version of 2. This is telling you that for all AP in L, there exists C in L such that C is less than or equal to A and C is less than or equal to B. Okay, and notice that we can work with the lattice. Oh, it's like the dual lattice. Okay, so because the definitions I have in there, this thing is written to so in the definition of direct set, we are going to kind of infinity, but it's not getting bigger. It's like, I mean, I have written bigger, but in the topological world, it's getting smaller and smaller. Okay. So in the subset notation. Okay. So that's the reason for this. And then the third property, we don't have this third property. But what I'm after is this theorem. Recall, I have a theorem like this. Let the theorem let X be a set and the delta be a collection of subsets of X such that so we have such that subsets of X satisfying following properties. Okay, so we have a bunch of properties here. Then tau is a collection of this sort. U alpha, alpha in here. Where B alpha. B alpha is equal to B1 intersection B2 intersection Bn for Bi is in B delta. Then this tau is a topology on X. So what we're after, so we have seen the definition of a subbasis for a topology. That means you start with the topology, right? And then we have a kind of the other direction. We start with a bunch of subsets of a set, just a set, and then you create this collection of sets. You take the finite intersections and then you take the arbitrary unions. Okay, and then you get a bigger collection, and we are asking what are the conditions on B delta so that this tau would be a topology. Okay, I think and I think what we want is have you seen a theorem like this in Moncrief? I think I remember. So the condition you want then there is a theorem like this in Moncrief. Have you seen this one in Moncrief? Version that's similar to this? Yes, no? Is this goes with the definition of a basis? No. So the point is like, so when we talk about a basis, we talk about basis of a topological space. Okay? And what we are trying to do here is we have a collection of sets, and then you I think you just generate a topological space out of that. So maybe this is have the notion of a topology generated by a collection of sets. Sorry. So this is the definition of a subbasis, but is that definition of a subbasis or like without referring to the topology. Yeah, so that's a situation. So the let me let me do this one. This is an interesting one. Okay, so we have this one. Uh, let let um, let's see, be a subset of Px. Okay, and this is like any collection of subsets. Okay, this is the theorem. Uh, show that tau of C given by tau of C that's given by intersection of all the so that this tau of C is the smallest topology that contains C. Okay, so this one, this is a very called uh, um, this is a very common trick, and you have seen this. It's like we can always construct a smallest topological space that contains this give like any given collections of sets by doing this. For example, you can apply the same process for if you have a group and you have big bunch of elements, and then construct the smallest group that contains these elements. What you do is you take uh, all the groups that contains those elements and you take the intersections. And it is easy to show that if you take any collection of groups and their intersection is also going to be a group, because when you have a binary operation and then whatever it's going to be, uh, it's going to belong to the that if you take two elements and you take the times operation, uh, whatever their product is going to be belong to each of the groups, so that's going to be in the intersection too. So it's this type of theorems holds for like any structure that you talk about, like uh, measures. You can say like if you're given collection of subsets, what is the smallest uh, sigma algebra that contains that? You just take the intersection of all the sigma algebras that contains that set. Okay, so but this one is But this doesn't tell you what a typical element of the tau C looks like. Okay, so and the one that we like is the one that is like this. So one that is like this. So this one is constructive. Okay, so we have particular way of constructing it. Um, so what we're saying, if we take for some collections like this B delta, and you can show that easily this tau is equal to the tau B delta. But not only that, we can actually describe the elements in here. Okay, so in order for this process to like create the topological space that might need some additional properties. I mean the I think in the uh, yeah, this is a simple thing, but what I'm after, I mean, we can actually verify. We can just go through uh, the proof and add conditions here. So for this thing to be a topology, we need the yeah, we need the empty set and the whole set needs to be in the topology. So I think you can get the empty set by picking the collection to be empty, and the whole set, for the whole set to work, so uh, uh, we need whatever the sets collections of elements in B delta to actually cover all the points in tau. So that means we want a union uh, of B in B delta of B equals X. Okay, so we need that. And then the empty set is there, the whole set is there, and closed under arbitrary unions is fine. Arbitrary unions is fine because it'll be like we have a collection of whatever, like capital lambda betas. Beta is in, yeah, so that's fine. And we need to worry about the finite intersections. So let's look into this. What is this property here? Okay. Yeah, let's look at these properties. Let's look at it in Piazza. Okay. But you understand like what I'm going at, and then see like whatever the conditions. I mean, you can get the condition by specifying a point, and but I prefer a condition that doesn't use the point, because the point doesn't belong to the lattice language. Okay. So okay, first you have a theorem that in this nature, and then you can mention the properties of, you can mention, basically you can use the fact that X is a set, and so the set has points, and you can talk about points. But in the uh, in the directed set world, or the lattice world, we don't have points, we have only neighborhoods. Okay. So, and this condition, the first condition is okay, because you can always throw in we can modify the lattice and you add the top to the lattice. Uh, that point is fine. What you're really after is this condition 2. And what I'm trying to get at, if you have this condition 2, and then you have so the exercise, find condition 2 star. Okay, then define b delta at the point x to be set of b in b delta such that x is in b. Okay. And I want this thing to be this is a directed set. Like this is the kind of the this is the kind of theorem I want. Okay. Any questions? Let's take a 5-minute break. Okay. Uh, okay. So let me explain what I mean. What do I mean by this? Like a way to kind of get the understanding. So I drew these 3 dots. Okay, here. Now, so I think now I have a way of talking about this. So in the topological side, we have these 3 things. So you look at you take so if you have X tau to be a topological space, you take B delta to be tau. Okay. And if you take B delta to be tau, we don't have to worry about these properties 1 and 2, and this should always create whatever the property you put there. It's going to be satisfied by B delta. Okay. And then you will get here, let me put like from here you go here, you get B delta to point X, but this is also still written in the topological language with the sets, right? Okay, these are like B delta X. These are some subsets of a set. Okay, and then you get this version in the lattice side. In the poset side, you get what I have written X. Okay, so you get to the point, and then in this line you get Ax. Okay, Ax is all the neighborhoods at the point X. Yeah. This guy. Okay, and if you take, instead of the whole topological space, you take this B delta to be a basis of tau, you can construct B delta X in this case, and what you'd get is what I wrote by Bx. So this B delta X would be the neighborhood basis at a point, and then you have Bx. We can like write the things in the lattice world. Okay. So the point is, you can write these things in terms of lattices, but this Ax and Bx would have more properties than a directed set. So what I'm after, what I'm claiming is this. If you start with the B delta to be a subbasis, and you like look at this thing. If B delta is a subspace, a subbasis, then of course this would satisfy, and this B delta would satisfy these conditions too. Okay. What I want to get here, this claim is like this should be a directed set. So these whatever the poset versions of these guys, they would satisfy more properties than what we need for a directed set. Okay. Now, so we'll work on this thing. We'll work on this thing more in plans. Okay. I don't know, this might be trivial, but might be very difficult too. Because remember, like we are still trying to bring in concepts from the topology into here. And we will have a theorem that goes the other way. Okay. We will create topological spaces with a lot of extra properties for example, in your Boolean algebra and so on and so on. Okay. So, but it is kind of as a starting point, it's good to analyze what happens at a point, and when you compare the directed set and the Boolean algebra, yeah, the directed set is going to be a Boolean algebra for sure. But we need the top and the bottom. Okay. Now, and then let's go through the next example. My next. And partitions. So we have P, these are partitions. Partitions of the interval AB. Okay. And this is where so now what you're trying to do is what happened when we did Riemann integration. We took a limit, right? And that limit is a little bit tricky. Okay. And okay, so we'll try to understand that. So let me so the goal is like we will develop so this would be example, and then we talk about all the usual limit theorems and everything, and we will kind of we write the general versions of lim sup, lim inf, and all that cases for the sequence. At the same time, we will develop the Riemann stages integrals. Okay, so this would be like two good examples. Okay, so now recall. So P, so let AB be subset of R fixed. Like it's not the infinite integral. So the partition P is a sequence of points T0, T1, T2, Tn, where T0 is A, that's T1, T2, strip B, and Tn that's equal to B. Okay? And n is greater than or equal to. Okay? Now, P and under the subset is a directed set. Okay? So because we take it's actually this thing is actually if we take two partitions for P1, P2, in here we have P1 this and P1 because basically you can take the unions and intersections, and I mean we only use this one, okay, in the theory, and this is called the, you take two partitions and you can concatenate, okay, not concatenate, you can what is it called, okay, you can throw everything in and like create the union, okay. Now here is a scary part, okay. So let me consider this sequence. Consider Pn. So let's take AB. Let me just 0 1. Okay, let's take Pn to be this set. Start at 0, go 1 over 2 to the n, 1 over 2 to the n minus 1, dot 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 1. Okay, and this this is perfectly perfectly nice sequence of partitions, but this is terrible to use for Riemann integration, because what we are really doing, you take the 0 1 interval and then you create the first partition. Yeah. So the first one has been in equals 1, you have 0, half, and 1, and then when n equals 2, you kind of break this part into 2, but you ignore this part. You're not kind of refining the other side, okay? And then you go here and you keep dividing, but it's okay. This is not gonna do the job for you, okay? And 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 the kind of the scary thing is you can use sequences, but you'll never get to infinity. You'll never get to the top of your directed set. This should be like really okay. This is a very, very, very scary thing, okay? And draw a little picture here. So you have the kind of the lowest partition that's it's actually call it P0. When you put when you put n equals 0, you have 2 to the power 0. That's 1. Okay. And then you have P1 and so on and so on. But it'll never get to the top. I mean, there is no top in this directed set, but the infinite that we are after is not this. Okay. So the takeaway is when we develop the Riemann integration, we took a limit, but that limit was a serious limit. Okay, and we had like a whole bunch of tools to do it. Let me let me stop here, and I'll continue next time. But I'll give you a exercise. Okay, little bit long exercise. You read. Rudin. You have the Riemann Stieltjes integral. Okay, and then you try to figure out what was going on. Okay, so you kind of start with this, and yeah. So let me do some stuff to kind of help you with this thing. So let me define P tilde. P tilde is we call it pairs P and C, where P is a partition and C is just a vector C 1 to C n such that C I is in the interval di minus 1 for I equals 1 up to n. Here P is the d0, d1. And then so this is like the when you define the Riemann sum, so there is a couple of things going on. So let's consider this map pi. You have from here to here, which is just defined by P, because C gets mapped to P. Okay, and because you have Riemann sums, but with the Riemann sums you kind of introduce the supremum and the infimum in the interval. Okay, and then so given f and alpha, we have these maps actually P tilde going from P. So this is what you really want. You want to define, so in here you have two maps. You have upper sum of F upper sum for the partition P, U F alpha P, and then you have the lower sums, F alpha P. Okay, but also you can define this guy, just the sum. Let's call it sum F alpha P delta. Okay, so the F alpha P delta is sum F alpha P delta is just this sum. So my equals 1 up to n f of Ci, and we have the delta alpha of Ti minus 1 minus alpha of Ti. Okay, and for the upper sum and lower sum, you kind of, instead of this number, you have the supremum and the infimum in that interval. Okay, so there is some sort of sandwich theorem going on too. Okay, so, and one little thing is this P tilde is not partial order. Sorry, P tilde is not a directed set. I mean, it is tempting to define the ordering of inside P delta by just using the one for P, but then it's not going to be, it's not going to have the property. If alpha is less than or equal to beta and beta is less than or equal to alpha, then alpha equals to beta. Okay, so you're not going to have that property. But keep in mind, like the real object that we are after is one upstairs, and then there's one downstairs, and the object in the upstairs get trapped by these two maps in the downstairs. Okay, and read the theorems in there, but ask the questions. Like you start the kind of from this perspective. You have a P, and that is a directed set, and now you're trying to compute a limit in the directed set. Okay. Good. Well, yeah, the word that I was after was the refinement of two partitions. Okay, so I think I'll stop here, but kind of have a big assignment. I want you to read the Ruding's book, Baby Ruding. It has a chapter on Riemann-Stieltjes integrals, and read it, but read it with this mindset, and then yeah, so you wanna think of this P as a directed set, and then you're taking the limit over that directed, something defined on the directed set. Okay, something that defined on a directed set is called a net. Okay, but I want you to read it and then kind of yeah, Yeah, read through it, and I think the analysis parts, all the estimates and all that, that's should be difficult. But the key part is now you're paying attention to the directed set part. Okay, let me pause the recording and